All right, so in part A, you've got, you're just solving for the weight, which will be equal to the force involved in this problem. So the weight is going to equal mg. So we're going to put in 5.4 kilograms times 9.8 meters per second squared. And what do you get for that? 52.9? 52.9? All right. And notice the work here. Notice that when you're doing these, because I'm not seeing enough work sometimes with some of you. You're just like putting numbers down on the page. Here's the formula that I'm using, W equals mg. So I know that if I have this, these two numbers represent m and represent g. So when you're doing it, make sure you begin with the formula that you're working with. So now that we know the weight, the question is, what is the work that's done on the box? So work, and again, we're using the same variable that we just used up here for weight. So weight and work, they have the same variable, but the thing is, weight is measured in newtons and work is measured in joules. So I know that's not work because it wouldn't be giving me an answer in newtons. So in solving for the work, it's saying that the box is lifted to a height of 7.8 meters. Well, if it's lifted to a height, then work was done. And since the weight is a vertical force, this is a vertical force needed to lift it, and we're lifting it vertically, 7.8 meters, then that's the number that I'm going to use. So I'm going to say work equals F dot D. But my F is this number. That is the force. So that's the force needed to lift something that weighs 52.9 newtons. So you're going to have 52.9 newtons, and you're going to multiply that by 7.8 meters. And if you multiply those together, you get 413 joules. So 413 joules. Now, the next question says, what potential energy will the box have when it's 7.8 meters above the ground? Well, when it's 7.8 meters above the ground, all the energy is potential energy. So if I begin with my law of conservation of energy, I have KO plus UO plus W equals KF plus UF. So that's my formula. You always begin with that formula. Well, when it was on the ground, how fast is it moving? 0, right? It's at its low point when it's on the ground, so what's the potential energy? Also 0, right? And then I do work between going from where I begin to where I end. There was work that was done. That's how much work we did. So I started with no energy. It was on the ground and it wasn't moving. When it reaches its maximum height, which one of these is going to be 0? When it reaches 7.8 meters above the ground, which one of these is 0? KF. So that's 0. So all it tells me is that work equals my final potential energy. That's what I'm solving for in this part. Part C says, what potential energy will the box have when it's 7.8 meters above the ground? That's this. So it says work equals that, and we just solved for work in the previous step. So what do you think the answer is for this? What? Same thing, 413 joules. So lift this up a little bit. So then in part D, it says, what will be the kinetic energy of the box as it hits the ground? So again, we're going to start here. KL plus UO plus W equals KF plus UF. Same formula, but now we're starting where the original position is when it's in the air, and the final position is when it hits the ground. So when it's in the air, how fast is it moving when I'm holding it in the air? It's not moving. So what's the original kinetic energy? So that's going to be 0. Does it have potential energy? Yes. Now we ignore air resistance. So is there anything to reduce the energy as it falls through the air? What? No. So this is also 0. When it hits the ground, which one of these two numbers will be 0? UF will be 0 because when it hits the ground, it's at its low point. You only have potential energy when you're above the ground, so when you hit the ground, it's going to be 0. So look at this. UO equals KF. So the only thing left, UO equals KF. Well, UO is what the potential energy was. Over here, we called it UF because we were starting on the ground and going to the maximum height. Now we're at the maximum height, so that number is our UO. So the question is asking, what will be the kinetic energy as it hits the ground? So what will the answer be for part D? 413 joules. So the KF will equal 413 joules. So all three of these numbers. This was the work that created the energy. Then this was the potential energy it had when we were at 7.8 meters above the ground. And then when we let go of it, all of this energy was turned into kinetic energy. So they're all 413. Now part E says what will be the speed of the box when it hits the ground? Well, now I'm going to use the formula for kinetic energy that involves velocity. So kinetic energy is 1/2 mv squared. And we're talking about the final kinetic energy, so we'll be solving for the final velocity, which is the velocity when it hits the ground. So our starting position is when it's above the ground, and we're finishing when it hits the ground. It's always important to identify where am I starting and where am I ending. So if I rearrange this equation to solve for the final velocity, I am going to multiply both sides by 2, so I'll have a 2 up here, divide by m when I bring that over, and then take the square root. So when I rearrange this equation, I'm going to have 2 times the final k over m, and that's going to be the square root. So that's what I get when I rearrange this equation to solve for the final velocity. That's the algebra. So now, and we should get our answer in meters per second. So when I write my joule, I'm probably not going to write it as a joule. I'm going to break it down into its fundamental quantities to show that I get the right units. So we're going to have 2 times 413, but instead of joules, a joule is a Newton meter, and a Newton is a kilogram meter per second squared. So a Newton meter then would be a kilogram meter squared per second squared. So that's my units that are equal to, so this thing right here is equal to joules. I'm going to divide that by the mass, which is somewhere up here. The mass was 5.4 kilograms. So you can see the kilograms will cancel out. Kilograms will cancel out, and I have meters squared per second squared under a square root sign. So I will get my answer in meters per second, and the answer comes out to be 12.4 meters per second. So this, what I have here, that's the velocity when all of the energy is kinetic. Now, if you look at the very last question up here, the very last question is, what will the speed of the box be when it's 3 meters from the ground? So it hasn't reached its full, its full 12.4 meters per second. It's going to have a little bit of potential and a little bit of kinetic. But I do know that those two numbers of energy have to add up to 413. So the last step to solve for that is going to be F is going to be KO plus UO plus W equals KF plus UF. I will finish going through this as you're leaving so that it's all in the podcast. Okay? What I want you to do is do number 5 and 7. So the assignment is 5 and 7. 5 is very similar to this one, and 7 you should be able to figure that one out. So if I complete this, when it was dropped, there was no kinetic energy, it was all potential, there was no work, and we're going to have two different sources of energy as it falls. So I'm going to get mg times the original height equals 1/2 mv final squared plus mg final height. And I'm solving this for the final velocity. So first of all, I can get rid of the masses. And I'm going to multiply through by 2 to get rid of the fraction. So 2 GHO equals VF squared plus 2 GHF. Solving for VF. I'm doing a podcast, that's why I'm talking to myself here. So VF is going to equal the square root of 2 GHO minus 2 GHF. Plugging in those numbers, and the final velocity is going to equal the square root of 2g times the original height minus 2g times the final height. So that's going to be g is 9.8 meters per second squared, 9.8 meters per second squared. The original height was 7.8 meters. And they want to know the velocity when it's 3 meters above the ground. So if we work that out, the final velocity comes up to be 9.7 meters per second. So those are the answers for each of these parts of the problem.